What's going on, everybody? We've been working with rational expressions for quite some time. That is, expressions not including an equal sign. We've just been simplifying rational expressions in so many different ways. We've been adding them, subtracting them, multiplying, dividing them, simplifying them, factoring them out. We've been splitting them every which way that we can possibly do and combining them anew. And in doing so, we are getting ready now to be able to actually manipulate these things towards the process of finding a solution, namely the solution to a given variable. So let's that's actually what's planned for today. Before we do that, let's actually take some time for ourselves here and to focus on our breathing for a little bit. This is intended to make us completely alert to the present moment here by clearing our minds, focusing on our breathing, taking some time so that we can be fully present in the moment. Take some time for that. Welcome back. Well, let's start in the land of the familiar with some, albeit challenging, problems here that remind us of the work that we were doing beforehand. We've got a couple of warm-up problems here that involve adding and subtracting some rational expressions. This will get us really warmed up for the processes that we're going to be going through today, and it's going to help us reinforce some of the learning that we've done in previous sections. Take some time for that. Welcome back. Well, in particular, the second of these two problems was probably the more challenging of the two, but still the first one was pretty challenging. Probably the keystone moment of it is in calculating this least common multiple for the least common denominators for all three of these fractions here. Taking these two factors here, this one is paralleled by this one is paralleled by this one, so we have x plus y, x minus y, and we also have a lone 2 over here that needs to similarly be included in the least common multiple. So that's our least common denominator here, appearing in all three of the fractions. We only have to double the top and bottom here of this middle fraction in order to get it to that point, but for here we have to multiply it by 2 times x minus y, and this one just times x plus y. We eventually do the distributive property and combine all of these things together into a singular fraction. Combining like terms, all the x's drop out so that we have negative 6y over this, and there's a factor of 2 that can cancel top and bottom here so that we just have negative 3y over this. In the same way, we have two denominators over here that can factor out. It takes a few steps in order to do so, but we have 4n minus 1 times n plus 2 for one of them, and for the other one we have 3n plus 1 times n plus 2. We have a common n plus 2 in both of them. We have to include this 3n plus 1 here and the 4n minus 1 here in order to get our least common multiple for the least common denominators for both fractions. In converting these two fractions together, we have to multiply top and bottom of this first fraction by the factor of 3n plus 1, and here we have to do the same thing with the factor of 4n minus 1. We then are able to combine these things into a singular rational expression in which we combine everything up and combine like terms, and we are left with this. Okay, so let's talk about the difference between rational expressions and rational equations. And to a large extent, you probably already know this because you've seen this in the context of algebraic expressions and algebraic equations. The difference is simply the presence of an equal sign. The smaller word inside the word equation is the word equal, indicating the presence of the equal sign here. And this may be something you might seem to be something that's pretty minor, but in reality it's pretty major, because these expressions we can only simplify. We can only play with them and add them and subtract them. We can't actually find out what the value of k is in this case, or the value of any other variable. It's only when we have an equation that we can actually solve for these variables here. So we can only solve equations, we can only simplify expressions. So here's an example here. Let's actually solve this. For the first time, we're solving these things. So let's take a look here at all three of these fractions, and let's ask ourselves, what's the least common denominator of all three of these? The answer is 3a. We have a factor of 3 here, a factor of a. The only thing that all of them go into is a common denominator of 3a. And in order to do that, we want to actually do this. If we multiply all three of them by 3a, we can actually knock out all three of the denominators here. This is kind of a different approach to the least common denominator here. If we multiply everything by this, we can actually remove all the denominators. And in doing so, the 3's cancel here, leaving behind just a times a, or a squared. The a's cancel here, leaving just 4 times 3, or 12. And the 3's cancel here, leaving behind 13 times a, or 13a. We then just have a simple quadratic equation that we can work on solving here. This is going to be a double bubble type solution here. A and A, the signs are going to be the same, and they're both going to be minus signs here. And so what are two numbers that multiply to give us positive 12 but add to give us negative 13? The answer is negative 1 and negative 12. This allows for us to then solve for A. There are two possible solutions, 1 and 12. So here's the solution steps for doing these things. If possible, factor all denominators. Make it so that you can describe these things in terms of factors. That will make it so that it's easier to combine them. You can work with them more simplistically. Write down the least common denominator of all the expressions in the denominators, and then actually get rid of all fractions in the equation by multiplying both sides of the equation by the least common denominator, and that will eliminate all the denominators. And then lastly, we can just solve the equation just like any other equation. At this point, it becomes just like the kinds of equations that you've been working with previously. We can also check the solutions from the original equation. Remember, you can always check your solution by simply taking your answer and plugging it back in for those variables at the start of the problem. Okay, so here's the first one to try a hand at here. We've got two terms here that are rational expressions. That is, they have something in the denominator. So ask yourself the question, what can I multiply every term on both sides by in order to rid myself of all fractions? Take some time on that and to solve this equation. Welcome back. Well, this is a great problem to help us in the process of learning how to solve these algebraic equations here. What we're seeing here is finding the least common denominator here, which is 2c, multiplying everything by 2c. All of the rational expressions go away, and we're left with a quadratic equation, which we can solve by setting everything equal to 0 and factoring things out. Our two solutions are -8 and +6. Now, there's something here that you want to keep in mind when you're doing these kinds of equations, and it harkens back to the fact that when we were working with functions, one of the things we had to take a look at was the domain and range of some of these functions. In particular, when you were looking for the domain, there was something you had to search out for to see if there was anything to be excluded from the domain. In particular, you were looking for anything that would cause a denominator to go to 0. And that's actually something that you'll want to check for each one of these solutions at the end here. So checking your solutions when you're done, it's been a nice little amenity, a good thing, a check in previous algebraic equation solving. For solving rational equations, it becomes essential because you want to make sure that none of those solutions are such that they will set that denominator to 0. If it does, it has to be disqualified as a solution here. So we'll see that coming up in just a moment here. Let's come back to another problem here. Here's an example. 3 minus 3 over x plus 3 is equal to x over x plus 3. So in this case, it's pretty easy to find what the least common denominator is. There's only really one denominator to work with here. It's x plus 3. So if we multiply everything by x plus 3 here, these fractions are going to go away, and I'm just left here with 3 times x plus 3 minus 3 is equal to x. Well, this is not going to take much in order to solve it here. Let's distribute 3 into these two terms here. 3x plus 9 minus 3 is equal to x. That becomes 2x plus 6 is equal to 0. 2x is equal to negative 6, and so x is equal to negative 3. Now take a look at this solution here and ask yourself if there's anything wrong with that. That's right, hopefully you can see this. This value of x makes the original denominators go to 0. That means it cannot be included as a solution here. So there is no solution. The answer here is, this is called the null set, which means there are no solutions to this particular equation. Okay, so it's a good idea to watch for that, and you can have some more practice here doing that very thing with this particular problem. Take some time for that. Welcome back. Well, we saw another instance in which we solved a rational equation rather for a what looked to be a solution, but as it turns out, this is a solution, quote unquote, that when we plug it in to the original equation, it makes all the denominators go to 0. That can't be allowed. It's not a part of the domain, so it can't be considered as a solution. Okay, so here's just another example here. It's going to be a little bit more complex. We're going to get 2 solutions out of this instead of 1. And so let's go through the process here of doing this. What is our least common multiple here of all 3 of these denominators? Well, probably the most complex one here is this one. If I factor this out here, I'd get 3 times t plus 2 times t minus 2. We see a t plus 2 paralleled over here, and the 3 is over here. So really, this is our least common multiple here that we want to multiply everything by in order to rid ourselves of all denominators. That's our least common multiple, and if we multiply everything across here, it looks pretty crazy when we do this, but a lot of stuff is going to cancel as a result of this. 1/3 times 3, that's all going to go away. We're just going to have these two terms here. T plus 2 and t plus 2, that's going to go away. We're just going to have these two factors. I should have said factors over here as well. And then lastly, this is going to cancel down here with all of this, leaving behind just t plus 14. All right, here. So here's this and this and this. We're going to FOIL all of these things out here. This is going to be pretty easy. It'll be t squared minus 4 minus 3t plus 6. Remember, we want to distribute that minus sign to both terms here. So this is not going to be negative 6. It's going to be plus 6. And that's equal to t plus 14. And if we get everything on one side of the equation and combine like terms, we'll have t squared minus 4t minus 12 here. So here we want to try and solve this for t by factoring things out, doing our double bubble. And as it turns out, what are two numbers that multiply to give us negative 12 and add to give us negative 4? The answer is negative 6 and positive 2. And when we set each one of these things equal to 0, we get t minus 6 equal to 0, which means t is equal to 6. Or we get t plus 2 equals 0, which means that t would be negative 2 here. So once again, we want to try and test each one of these values for both of these, for plugging into this equation. I can already see here that plugging in this negative 2 will make this denominator go to 0 here, so we can't include that one. But if we plug in 6, let's see, 6 plus 2 is 8, that's fine. 6 times 6 is 36, times 3 is, oh good grief, it's going to be 108 minus 12, and that's going to be 96. So it's certainly not going to 0 there either. So there's only one solution that's left behind here, not the minus 2. We had to lose that one, but we kept t equals 6 as our only solution there. Okay, so take some time for this one. Again, it's the same idea here. Really, the only thing that we've added to this process is remembering to check our solutions to see if any of them cause the denominator to go to 0. Everything else is pretty much the same. Take some time for this. Welcome back. Well, once again, we had to disqualify one of our solutions because it caused the denominator to go to 0 here. In this case, it was the solution -3, which we got from doing this double bubble factoring out of this trinomial here, and that had to be removed because it makes particularly this denominator go to 0 here, leaving behind only one possible solution, n equals 4. You can actually already begin to see here that you're going to have something that one of our solutions is going to drop out here, because as we're solving this for 0, we're saying n plus 3 is equal to 0 to get this -3, and as you can see, we cannot set n plus 3 is equal to 0. So you can already start to see the disqualification happening here at this stage. Okay, just getting more complex here. We have a major trinomial here to factor out. Actually, there'll be a greatest common factor here to be removing from all three of these terms before we even start that. There'll be similar greatest common factors to do the same thing with these terms as well, but take some time for this. Actually, I'm going to do this here. This isn't one for you to do. This is one for me to do. So let me work on this one here. So let's start by factoring this out here. 6 times n plus 1 times n plus 2. Okay, very good. This is going to factor out to 2 times n plus 1, and this is going to factor out to 3 times n plus 2. Well, we can see n plus 1s are in common, n plus 2s are in common, and then we have 3 and 2 and 6 here. So really it's this that is our least common multiple here. 6 times n plus 1 times n plus 2. This goes into this, and this goes into this as well. This is our least common multiple here. It's what we're going to multiply all terms on both sides by. And when we do that here, a bunch of stuff is going to cancel on this left-hand side, leaving behind just 5. And in this term here, all the n plus 1s are going to cancel. 2's going to cancel with the 6 to make it a 3. This is going to cancel out the n plus 2's. The 3 is going to cancel with the 6 to make it a 2. And the result is that we have a significantly more simple equation here to work with. 5 is equal to 3n times n plus 2 times n plus 1. We have to use the distributive property a couple of times here. We'll get 3n squared minus plus 6n plus 2n plus 2. Let's combine like terms and set everything equal to 0. 3n squared plus 8n minus 3. All right, so for this we want to ask ourselves, let me actually get out my pen here. I make one of those handy-dandy little x's here. We want to know what numbers multiply to give us -9, that's 3 times -3, but which add to give us +8. And the answer, the only answer to that, is 9 and -1. If you multiply these two things together, you get -9, but if you add them together, you get +8. So this 9 and -1 split this 8 here into 9n minus n. So now we have 4 terms on here. The first 2 terms, we can factor the greatest common factor out of those, and we can do the same thing with these 2 terms here, and we'll get 3n times n plus 3 minus this same quantity n plus 3. So now if we factor out the n plus 3 from these 2 terms, we're going to get 3n minus 1 times n plus 3. Again, that's being set equal to 0, so then we can set each one of these factors equal to 0, and let's see what we get here. N plus 3 is equal to 0, or 3n minus 1 is equal to 0, and so these are our 2 solutions here. And I'm looking on this, I can't see, let's try the -1 here first. 3 times 3 is 9 plus 6, that's okay. 2 times 3 is -6 plus 2, that's not 0. 3 squared is 9, 9 times 6 is 54. 3 times 18 is 30, no, this is embarrassing. It's 54. So this is, we started off here with 54 minus 54 plus 12. So that's still a denominator that's not 0. So -3 checks out. 1/3 here, this is going to be 1/9. So this is 2/3. That's not going to, 2/3 plus 6, yeah, that's not 0. 2/3 plus 2, that's not 0. 3/3 is 1 plus 6, that's 7, that's not 0. So both of these solutions here work fine. They don't make any of those denominators go to 0, so both can be included as solutions to this equation. Okay, try this one here. It's very, very much like it. Big thing will be factoring things out and creating your least common multiple. Take some time for that. Welcome back. Well, we've done the first of three parts of today's lesson. The first lesson here was the most significant one of the three, the most challenging one of the three. That's where we solved for the first time a rational equation here by multiplying all terms on both sides by the least common multiple of all denominators, and in doing so solving the equation, remembering to check each one of our solutions that it doesn't disqualify itself as part of the domain by setting one of the denominators equal to 0. Second, one of the things that we wanted to talk about was solving a proportion. This is just an alternate tool in your toolbox to solve some of these rational equations here. And you can see an example here of a proportion. The way I sometimes think of a proportion is that, if you've got a recipe here that involves, let's say you're making cookies here, and this involves 9 cups of flour and 5 cups of sugar. There's a lot of cookies you're going to be creating here. And you want to basically double the recipe. What you're going to be creating here is something that involves 10 cups of sugar and 18 cups of flour. Now that might seem trivial here, but you could also do something like this, 7.5 cups of sugar and 13.5 cups of flour. That's 1.5 times each one of these things here. That's also this is also something that has the same ratio here between these two numbers here. And so this is actually a proportion. This is also a proportion here in which we have two ratios that are set equal to each other because they are in fact equal. And so when you see rational expressions like this set equal to each other, and it's just one rational expression on either side, then you can think of them as a proportion, which is nothing more than two ratios set equal to each other. And what you can do with these proportions is you can do a little bit of a shortcut here with these, and that is that if these two ratios are equal, then this times this has to be the same thing as this times this. We call this cross products, and we describe it using this template. We describe it this way: A times D is equal to B times C. And so for this proportion that we have on top here, we multiply 18 times 5, that's going to be 90, and we multiply 9 times 10, that's also going to be 90. So you can see it works here. 90 is equal to 90. Let's see how we can use that for problems like this here. If I take these two rational expressions that are set equal to each other, cross products here can be helpful. 20 times d, that's this first cross product, is equal to 8 times d plus 6. 8 times d plus 6 is here. And the rest is just distributing, simplifying, and solving. And here once again we're going to check our solution here to make sure that it doesn't set any denominators equal to 0. That solution is fine. Alright, so here's one that you can similarly do yourself. Try this new technique as well out for yourself. Welcome back. Well, we can see how cross products really provides us a shortcut way of solving all of these rational expressions. When we've just got one on either side of the equal sign here, we can think of this as just a proportion, and so we can do cross products to find a quick solution here. And by checking it, we don't see any instance in which this will set any denominator equal to 0. So this is our final solution here. Well, that's actually the first and second thing that we want to cover in this particular module. The third thing has to do with what do we do when all we see are variables in these particular equations. What do we do when we're faced with what's called a multivariate equation? That's something that looks like this. We don't see any numbers in it whatsoever. Everything is a variable. This is one of those things that looks completely different, and actually it's exactly the same. We look at this and they say this is totally different, it's totally unfamiliar, and this is the part where Yoda would say, no different, only different in your mind. So this is a place in which you will actually see that doing the same things that we did before will allow for us to solve something like this. If we want to solve for a particular variable and get this variable by itself, how would we do this? Well, what would we do if we had a minus 2 here and a number here and a number here? We'd do the exact same thing as this. We would multiply both sides and by a minus a here, making it so that this denominator disappears. It's going to cancel out over here with this one, leaving behind just m times a minus a is equal to x. That's at least going to get this variable out of the denominator here. And then let's actually divide everything. Well, let's distribute the m here. That's fine. If we distribute the m here, we have ma minus m times capital A is equal to x. If we send the m capital A over here, that's fine. Then all we have to do is divide everything by small a, and we are finished here. So it's the same set of procedures here. It's the same set of relationships, the same patterns as before. We're just dealing completely with unknowns here. This is what makes it kind of cool and fun. So try this one here. In this instance, you're given a multivariate rational equation here, and you're going to solve specifically for D. Take some time for that. Welcome back. Well, I'm showing you the solution in one of its forms, but I'm actually mindful of the fact that some of you might have done this problem slightly differently. When I'm looking at this particular point right here, noticing that we want to solve for D, perhaps what you did is you divided both sides here by y. That's totally okay. And if you did that, then these two things disappeared, and that gave us r plus d is equal to c over y. That's okay. And then solving for d just involves subtracting r from both sides. D is equal to c over y minus r. Now that looks totally different from what we've got down here until we start to split this up into two different fractions here. Two different fractions, c over y minus yr over y. Well, in that case, the y's cancel, don't they? So this is just r. Look at that. It's the same thing here. So this is another form of the same relationship here. Either one of these is a correct answer here. So if you did it this way, don't feel bad. That's also a legitimate manipulation of this multivariate rational equation here. All right, so let's do one more of these kinds of problems here, one that's got more than one denominator here, so it becomes a bit more complex here and a little bit more challenging. In this case, we've got three denominators that we're working with. All three of them are unknown, so we can't assume that there's any common factors among any of these three denominators here. We want to specifically solve for b. So in this case, in order to find the least common multiple, we're just going to multiply all these things together here. We're just going to multiply everything times a, b, c, and that's going to knock out all three of these denominators here. It's going to leave behind a little bit of a mess. BC plus AC equals AB. Again, we're solving for B, and we've got B in multiple places here. We're going to want to get all the terms with B on one side of this equation here, and then factor out this B. And we'll also want to send everything that does not have a b in it to the other side of the equation. So let's do that here. We've got AC sitting here, and these two terms have a b as one of their factors here. We can now factor out a b here, and what's left behind is a minus c. So now in order to get b by itself, we just have to divide both sides here by a minus c, and this is what we get here. We have solved for b. So notice, even when we have nothing but stuff in the denominators and just ones everywhere, we can still solve for b here by simply multiplying all of the terms on both sides of the equations by the product of all three of the denominators in this case. That's our form of the least common multiple, and as you can see, that gives us the an equation that solves this solves everything for b and manipulates this relationship in a way that allows us to see what its relationship to b is. All right, this is the exact same equation here, except this time you're solving for a. Take some time for that. Welcome back. Well, that procedure was pretty much the same procedure that you did in the previous problem here, where we multiplied everything by a times b times c to get rid of all the denominators in all terms, and in doing so we got a very similar expression when we solved everything for a. Okay, so in summary, we've hit the place here. We're here. We've actually used all of these things now to start solving these rational equations here, solving for values of variables. So that was probably the biggest thing that we got to today, is solving these rational equations. As you probably found, it involved little more than the skills that you already have from previous classes here, and your skills also from earlier versions of algebra that didn't involve rational equations. Things like factoring stuff out and combining like terms. All that stuff presented itself here as well. Once you solve the rational equation, probably the biggest thing to remember was that you have to check each one of your solutions to make sure it doesn't set any of those denominators equal to 0. Second thing, when you've got an equation that has just two rational expressions in it, one on either side of the equal sign, you can treat them as a proportion, do cross products, and get rid of all of your rational expressions that way. So you just have two things being multiplied together on either side of the equal sign there. That'll simplify things and speed up getting a solution. And then lastly, you did the same thing here with equations that had multiple variables in them. In fact, nothing but variables. You worked with that as a means of solving a multivariate rational equation for a specific variable. And in doing so, you were manipulating that relationship so that you could see it from a different point of view. This is the stuff we've been covering here. You are now prepared for the assignment, and I hope to see you in class soon.